Okay, so as you might already see, this is all about alkyl halides, chemical reactions. This is organic chemistry. Let's begin first with the definition. So, what are alkyl halides? So, alkyl halides are organic molecules that contain a hydrogen atom. Usually, this is represented as X. So, halogen group in the periodic table. We have chlorine, bromine, iodine, fluorine. So yeah, the halogen group, and it is bonded to an sp3 hybridized carbon atom. So what we mean by sp3 hybridized is when it comes to geometry, it is tetrahedral. So the carbon is connected to 4 groups. So yeah, the halogen atom in halides is often denoted by the symbol X. That's what I just said. It is alkyl halides are classified as primary, secondary, or tertiary. So each one there is a difference when it comes to defining them, uh, especially in regards to the Sn1, Sn2, as well as the E1, E2 reactions. So more on those later. That's pretty much a big chunk of this lesson, those reactions. So what are other types of alkyl halides? So we have vinyl halides as well as aryl halides. Aryl halides, you see a ring, a benzene ring to be specific. And vinyl halides, when the halogen atom is bonded to a carbon-carbon double bond. So when we say double bond, this is not sp3 hybridized, rather it's sp2. So yeah, they are unreactive reactions. So what about the naming of alkyl halides? So first things first, actually when we say naming, at least in my institution, the standard is you're supposed to follow the IUPAC way of naming. So yeah, it is similar to uh, naming hydrocarbons, stuff like that. So you of course find the parent carbon chain and you name it as an alkane. You know that it is the parent carbon chain when that chain has the most number of carbons possible. So yeah, you name the halogen as a substituent. So as far as I know, these are the only halogens that you will be dealing with for the most part. So F, you have fluoro, Cl is chloro, Br bromo, I is iodo. So yeah, what is the name of this? What's the name of this? So you have 7 carbons in the longest chain, so that's hept. Actually, the answer is already here, but where do we start counting the number of carbons? From the right or from the left? So there's another policy. It's not here, but when you see a substituent that's closer, right now we see a substituent that's closer at the right side. So C1, C2. If we counted from the left, C1, C2, C3, only by the time you reach the third carbon will you see a substituent. So ideally you prefer this. So yeah, at a carbon that's denoted with a lower number, so C2 instead of C3. So how do we name this? 2 chloro what? 3, 4, 5, 5 methyl. Chloro comes first because by alphabet uh, C is mentioned earlier than M, right? So 2 chloro 5 methyl heptene. That's exactly what's said here. So yeah, you apply all the other rules of nomenclature. So you number the chain. Um, you begin at the nearest. You begin at the end nearest the first substituent, either the alkyl or halogen, and you name and number the substituents. So, okay, this is not related yet. Um, we'll talk about this later. So, what are common names for alkyl halides? Here often for simple alkyl halides, always IUPAC. And when you assign a name, you have to name all the carbon atoms of the molecule as a single alkyl group. You name the halogen that's bonded to the alkyl group, and you combine the names of the alkyl group and the halide, separating the words with a space. So, okay, what are we seeing here? A tert-butyl group, no? And iodine becomes iodide. So, the name is tert-butyl iodide. Don't forget the small dash. And yeah, coming from chlorine, it becomes chloride. And since we have two carbons in the parent chain, this is an ethyl. When we actually wait. So when we call the carbon chain a group, so here it's ethyl group, here it's butyl group for carbons, the halogen is automatically pronounced with a D at the end, not an N. So chlorine becomes chloride, iodine becomes iodide. So, okay, let's talk about physical properties of alkyl halides. So, most of these alkyl halides are soluble in organic solvents. So at the same time, they are not soluble in water. So alkyl halides are weakly polar molecules. So technically they are polar, and when we say polar, what comes to mind is that this particular molecule is capable of hydrogen bonding. But then in the case of alkyl halides, they actually are not capable of hydrogen bonding. So more on that later. Let's go to the two main properties first. So when it comes to the boiling and melting point, alkyl halides have higher boiling points as well as melting points compared to alkanes. So hydrocarbons, single bond, having the same number of carbons. So, okay, that's self-explanatory. It's understandable. When the melting and boiling points increase, you know that the size of the R group would also increase. So expect to hear more about the R group. So here we have more specific examples. Obviously, if you have more carbons, in this case you have 3, here you only have 2, it gives you the idea that boiling point as well as melting point increases. So it's basically like adding more water on a pot, on a metal pot, and you're trying to boil it. Of course, if you add more water, in the same logic, when you add more carbons, it's gonna take a little longer, assuming you're burning with the same. Assuming that you're boiling with the same temperature. The time that it takes to boil the water. So yeah, as you can see, it's very easy to distinguish because the halogen is the same, it's chlorine. But then what if they are not the same? It brings us to this trend. So As the size of the halogen increases, the boiling point as well as the melting point also increases. So what's the trend in the periodic table? Let me just verify. So in the periodic table, the size of the halogen atom increases as you move down the periodic table. So coming from fluorine to astatine, uh, but like essentially, fluorine has the lowest boiling point, and iodine. So it's basically a ranking, okay? Followed by chlorine, bromine, and then iodine. Iodine has the largest size. So um, at the same time, when your boiling point as well as melting point increases, the halogen becomes more polarizable. What does polarizability mean? Okay. The explanation is pretty complicated. It's not straightforward, but like since we all know that iodine is bigger compared to fluorine, so when we say more polarizable, that basically means iodine is a larger atom with more loosely held electrons. So it's basically easier to distort its electron cloud and induce a temporary dipole. Is there an easier definition for this? Maybe with respect to stability. Wait a minute. Anyways, let's move on. Just know that trend. When it comes to solubility, I've already mentioned this earlier. The alkyl halide, or denoted as Rx, by the way, is soluble in organic solvents, but it's not soluble in water. Why is that? I I think it has something to do with alkyl halides being weakly polar. Since water, for one, is a polar molecule, you know that it's polar because the electronegativity difference, when you compare oxygen and hydrogen, it's very different. Um, when it comes to hydrocarbons, they are nonpolar because the electronegative difference of carbon and hydrogen, the discrepancy is not so big compared to uh, between oxygen and hydrogen. So yeah, it is a little counterintuitive in that sense, knowing that alkyl halides are polar technically, but they cannot be soluble with water, which is also polar. it all comes down to the specific idea that they are weakly polar. So incapable of hydrogen bonding, so cannot be soluble in water. Okay. So aside from being weakly polar, they exhibit dipole-dipole interactions because of their carbon-halogen bond. So sure, I know this kind of interaction is weaker compared to H bonding, but yeah. Halogens, being more electronegative, pulls the electron density coming from the carbon. Okay. Since the rest of the molecule contains only carbon-carbon and carbon-hydrogen bonds, they are not capable of intermolecular hydrogen bonding. So it's just a more elaborate explanation of what's been said earlier. So since the halogen, being more electronegative, pulls the electron density, usually the halogen gets the partial negative charge. And at the same time, the carbon that's beside it becomes partially positive. So you can say from here that the carbon tends to be an electrophile. So what does um, it mean to be an electrophile? You're attracted to electrons. Okay. Yeah, it makes sense. When you're a partial positive, you tend to become an electrophile. You tend to desire um, negative coming from positive. Since you're partially positive, you desire negative. That negative is the electron. Okay. Reaction types on alkyl halides. When alkyl halides undergo substitution, they substitution reactions. It is together with nucleophiles. But when they undergo elimination reactions, that is to be with Bronsted-Lowry bases. So there's a difference you have to note. So the alkyl halide is going to be the substrate. The nucleophile is basically called, or the species that carries the leaving group. What is the leaving group in this example? So we have the halogen and basically the sp3 hybridized carbon. We call this the substrate itself. We have the nucleophile, designated generally as Nu minus. And then, so the nucleophile will go this direction. Sorry. So the leaving group, from the word leaving, it would leave this figure. And what happens is that the nucleophile will now sit on top of the sp3 hybridized carbon, which is what happened here. So it is important to know, to be able to identify what the substrate, what the nucleophile is, as well as the leaving group. So when it comes to undergoing elimination reactions, again, we don't, it would be wrong if you say that it reacts with nucleophiles. That only applies with substitution reactions. So namely Sn2, Sn1. For elimination reactions, we have E2, and E1. Okay? So elimination reactions, for example, we have this. Together with the base, elimination, basically we form a pi bond. Okay? And at the same time, the leaving group, as usual, um, will be on its own at the product side. The hydrogen over here will be bonded uh, to the Bronsted-Lowry base. And we have here, as a separate entity, the figure showing the pi bond. So the neutral halogen in the reactant side becomes negative, if you noticed, as the leaving group at the product side. So that is if it's neutral in the reactant, becomes a negative. If you noticed here, the halogen here was neutral. And yeah, it also became negative by the time it reached the product side. I am not sure if the other way around would also apply. Yeah, we'll see if we can make an observation later on. Substitution reactions, again, 3 components are necessary in a substitution reaction. You have to know how to identify those 3. That's namely the substrate, the nucleophile, and the leaving group. Leaving group is the halogen, usually. When it comes to, within the context of alkyl halides. So, yeah, this has been the same example earlier. Let's look at this first example. So we know that this one is the nucleophile. OH hydroxide is a strong base. Wait a minute. Are all strong bases nucleophiles? I don't think so. So strong bases could be good nucleophiles. Oh wait, no. I know that when it comes to basicity, a weak base makes a good nucleophile, or is a good nucleophile. Let me just confirm if that's correct, if I remember right. That's weird. Okay. It says you cannot conclude that weak bases are good nucleophiles. It leans more to the idea that strong bases are generally good nucleophiles. So yeah, essentially this is our nucleophile. This is our leaving group, the halogen. This is our substrate. Okay? So in the product side, so the leaving, the nucleophile attacks. Actually, I've been pointing it wrong. Supposed to point here at the carbon that's connected to the leaving group. And the leaving group is separated. Halogens are 1, 2, 3, 4, 5, 6, 7. They have 7 electrons, right? Wait. 1, 2, 3, 4, 5, 6. Ah, yes. So chlorine here is neutral. But because it's in this form, it's negative. Here, your nucleophile was negative, now it's neutral. Oxygen has 6, right? 1, 2, 3, 4, 5, 6. But like previously, 1, 2, 3, 4, it was only bonded to hydrogen. But when you bond it to the carbon here, the minus sign is removed. It becomes neutral. Second example. So this is another nucleophile. Another example. You put the arrow here. Oh yeah, I almost forgot. Going back to the first example, you don't just put an arrow here. You indicate that there's an arrow going to the leaving group. That's what indicates this one. The same thing here. So there you go. Iodine. It makes sense. There's supposed to be 8 dots. When this only has 7 dots, then it's not negative. But because you placed an additional 8 dots, an additional dot number 8, it's gonna be negative. You could say the same for in the case of iodine, since both of them are halogens, they are in the same group, having the same, having the same octet. I'm not sure if that's how you describe it correctly, but yeah. Here, this is your nucleophile, OCH3. And then your leaving group is the bromine. So it's pretty simple. Let's go here. Nucleophiles in substitution reactions. So nucleophiles are Lewis bases that can be negatively charged or neutral. Okay. So yeah, surely they are Lewis bases. And what determines a good nucleophile? So what's a good nucleophile is usually negatively charged. You cannot say the same for neutral counterparts. So let's have this example. Bromopentane. I think that's the name of this. And you have sodium hydroxide. But then, how do you identify the nucleophile if you're given sodium hydroxide? Simply, you consider, we already had an example that basically says OH is a nucleophile. So whatever's connected to it will just simply be considered a spectator ion. So it only spectates in a chemical reaction. So when you place an arrow coming from the nucleophile to the carbon connected to the leaving group, I think that's called the alpha carbon. Wait a minute, let me just confirm, just to be 100% sure. Okay, so yes, connected to a functional group. So the arrow here points to bromine. So you put the hydroxide, you replace bromine with the nucleophile, and the bromine goes together with the sodium, the spectator ion. So it would be wrong if you placed Na here. Since it is just a spectator ion, you just leave it as is. You don't bring it together with the nucleophile. Okay? That's the main idea. What if the nucleophile were neutral? So in this case, nitrogen, you don't have to put a negative sign anywhere. You see five connections. I mean 5 electrons. So you point to the alpha carbon, and then this line, this arrow pointing to the bromine. What you get is this. So you can determine from this reaction, or basically you can conclude that when your nucleophile is neutral initially, it can become positively charged. So 1, 2, 3, 4, yeah, positively charged. And your neutral leaving group becomes negatively charged. Okay, so here are the common nucleophiles. Again, good nucleophiles are the ones that are negatively charged. We have hydroxide, OR, CH3CO2 minus, N3 minus, cyanide, chlorine, bromine, iodine, HS, RS, H2S, hydrogen disulfide. This one's hydrogen sulfide, I think. Yeah, so neutral nucleophiles, we have water, ammonia, ammonium, RNH2, as well as ROH. So it's not that hard to remember. What if you have this? Bromoethane and water. If you so bring the leaving group is your bromine, your nucleophile is the water itself. It's the entire thing. So after changing their positions, this is actually not the final answer yet. When you see water, it has to be separated. And this is where, this is the continuation. An oxonium ion is defined as an oxygen that's positively charged. So, this is what I'm not really certain about. So essentially, in the end, one of them will be like this. But like, what happens to this hydrogen? The solution is you add another water. But like, is that supposed to be H3O? That's my limitation right now. So yes, the explanation is here. The extra hydrogen is very acidic, so it will force for the reaction. Basically, the oxygen wants to become neutral because it is oxonium. It is positively charged. The target is to have a neutral product. And having water or hydroxide as a nucleophile, you have to expect the urge to release an extra hydrogen. Okay? This is quite a lot. This is the second page. We have 6 of them. Okay? So, leaving group. In comparing two leaving groups, the better leaving group is the weaker base. Oh, okay. So this is actually what I was referring to earlier. I initially thought it was regarding the nucleophile. No, it's actually about the leaving group. So if your base is weak, then you have a good leaving group. For alkyl halides, the leaving group is always the halogen. Okay? But like, except for fluorine. What's the reason? So, if you recall, in the periodic table, the trend is when it comes to electronegativity, it is going up and going to the right. And the most electronegative element is fluorine. It had to be fluorine. So, knowing that, um, it's actually being the most electronegative atom, it is a very bad leaving group because it doesn't want to leave the molecule. So, that's basically what um, having a high electronegativity does. Um, so, yeah. Expect that you will only be seeing bromine, chlorine, iodine for the most part. So, okay, so this is a trend that you have to know. From left to right across the row of periodic table, um, basicity decreases, so leaving group ability increases. Again, when the base is weak, the leaving group, it is considered a good leaving group. So, yeah, compare water and NH3. Both of them have hydrogen, but like, uh, which is located at the left position. If you recall your periodic table, the order is like this: B, C, N, O, F, N, E. So coming from the third, fourth, fifth, sixth, seventh, and then eighth group. Uh, Nitrogen is right here. Again, from left to right across the row of periodic table, basicity decreases. So what's more basic is the nitrogen in comparison to the oxygen. Okay? So, yeah. At the same time, you'd say that um, nitrogen, being more basic, being a stronger base, oxygen is a better leaving group. Okay? So, down a column of the periodic table, basicity, basic strength decreases. So overall, it's shown here. Basicity trend. So if electronegativity is going up to the right, basicity is going up also, but to the left. Here, I was comparing the halogens. So up to down, the order is from up to down, it's fluorine, chlorine, bromine, iodine. Iodine is at the very bottom. And uh, it is the best leaving group because it is considered the weakest base of them all. Fluorine is at the very top, so yeah, makes sense. So what does it mean for iodine to be the best leaving group, being the weakest base? It basically means it can easily disperse negative charge around its electron cloud because of its big size. I think this has been mentioned earlier. Hopefully it makes more sense now. So, what are good leaving groups for nucleophilic substitution? So, we have chlorine, bromine, iodine, water. I think at this point you just have to memorize the list or at least be familiar. Good leaving groups, we have chlorine, bromine, iodine, water. For bad leaving groups, so one of them is fluorine, common sense. OH, hydroxide, is strong, a strong base, so it's not a good leaving group. I guess also this NH2 hydrogen and R. A very strong base will attack again and reclaim back the substrate. So that's what makes it a bad leaving group. Looking back at this list, chlorine, bromine, iodine. So everything in the halogen group except fluorine is a good leaving group. And we've seen it. We've seen it in the previous examples so far. Like we've been juggling with these leaving groups, with these halogens only. At one example, we had water, right? And water is polar. But it's not a strong base. It's a weak base. So that's what makes it a good leaving group. Okay, so let's now go to the mechanisms of the substitution reactions, nucleophilic substitution reactions involving nucleophiles. So, yeah, this is just a derivative of what I just said earlier. Okay? Oh man, this is a lot. This is a lot. Okay, for Sn2 reaction, this is in other words called substitution nucleophilic. So S, N, and then 2 means bimolecular. Bimolecular meaning the rate depends on two molecules. So if we consider this reaction, we have CH3Br or bromomethane. This is our alkyl halide. We have the halogen here connected to the carbon, alpha carbon. This is sp3 hybridized. We have acetate. This is our acting nucleophile. It makes more sense because we see a negative sign. In the product side, so this entire thing goes to the alpha carbon, and the bromine, the arrow coming from the line that connects CH3 and Br, there's an arrow going to the bromine. So bromine is the leaving group. So what is the definition of, how do you define Sn2 reaction? So kinetic data shows that the rate of reaction depends on the concentration of both reactants. That applies for Sn2 reaction. When you have, in this, wait. So it depends on both the substrate and your nucleophile. Let me just confirm the consistency of what I am teaching. Okay, yes, it is consistent. So, in other words, Sn2 reactions exhibit second-order kinetics. When we say second-order kinetics, the reaction rate depends on the two reactants that we have generally, namely the nucleophile and the substrate. Okay, so let's look at the mechanism of the Sn2 reaction. Also, you have to know that Sn2 will not happen if the leaving group and the nucleophile are faced in front of each other. So there's something called backside attack. Um, it has to lead to inversion of configuration. Okay? More on that later. Let's go here first. So the Sn2 reaction mechanism is concerted. That means when you look at a graph, you only have one mountain. Okay? When we move to Sn1 reaction, it's called a stepwise reaction. That means there is more than one transition state. Here, since it is a concerted reaction, we only have one transition state. So bond forming and bond breaking happens in concert or simultaneously at the same time through a single transition state. Again, that's for Sn2, single transition state, only one mountain. For Sn1 reaction, it's more than one transition state. So that's more complex in that sense. How do you draw the transition state? So this is your acetate. Initially it was negative, right? So you put a partial negative. And you know that in the product side, your leaving group became negative. So bromine here, the leaving group has a designation of partial negative. And okay, so this is your substrate, the CH3. It is in the center. And you have these temporary dashed lines. Similarly, I can't remember the specific term. Wait, let me just search what that is. It might help you visualize what we're looking at. That's what makes it very important. Resonance. Okay, yes. In a way, when you draw resonance structures, not just the resonance structure, more specifically what do you call that? I think it's called the resonance hybrid. It has these temporary dash lines. So yeah, that's part of the package. And don't forget the brackets and the double dagger. That's one unique characteristic of drawing a transition state. If you did not draw the double dagger and the brackets, don't expect to get any mark. That's how important it is. What is the meaning of the double dagger anyways? So it denotes, well, it is, in chemical kinetics, the double dagger symbol denotes a transition state. So yeah, it gives a very specific idea. So the transition state itself is characterized by being a specific unstable configuration of atoms that happens during a chemical reaction. So in the graph, you see that basically the transition state is located at the highest point of the mountain, which is here. So transition state happens at the highest energy point along the reaction coordinate. Again, what characterizes this state is the lack of stability. So what is the relevance of the transition state anyways? So it says it's important for predicting and manipulating reaction rates and outcomes. So yeah, essentially the goal for one of the goals of studying chemical reactions is being able to predict chemical reactions, and this is an important part in that process. So okay, let me show you this. So this coming from where you started here up to the highest point, it's denoted by EA. EA means energy of activation. Where did I mention that? Ah, it's not here. What? So this energy of activation is the minimum amount of energy that is necessary to initiate a chemical reaction. If you don't reach this specific amount, you won't reach the transition state, no chemical reaction will occur. So also the delta H here, if I remember right, it is standard, no, not standard. At least it's called enthalpy. In chemical engineering calculations, this is, we have something called delta comb H degree. So this means standard enthalpy of the combustion of fuel. Higher heating value is equal to its negative. I still got it. Also, 44.01T, this is a constant delta vape H water. The standard enthalpy of the vaporization of water. Kilojoules per mole of water. That's the unit. Anyways, that's not related to organic chemistry. Going back to org chem. In the transition state, the carbon-bromine bond is partially broken. And the carbon-oxygen bond is partially formed. So initially, the carbon-bromine bond, it hasn't been broken yet, right? But in the transition state, it's partially broken. And the carbon-oxygen bond, oxygen coming from the acetate, the nucleophile, so the bond is being partially formed. That's what this illustration means. So both attacking the nucleophile and the departing leaving group bear a partial negative charge. So it's this one. Again, how do you determine what partial charge to place? Here, it happens that the nucleophile is negative. So in the transition state, we show partial negative. The leaving group in the product side became negative, so we show that the leaving group is partially negative in the transition state. Okay? How about this example? This is a stereogenic center. Yeah. Deuterium, R group, hydrogen, bromine, 4 different groups attached to it. So again, what is it? What's supposed to happen so that you can call a carbon electrophilic? When carbon becomes partially positive. But you know that the carbon is electrophilic if it has a partial positive or a positive charge. But you don't see that in the transition state because it is a substrate. It is part of the substrate. You only see partial charges um, in the nucleophile as well as the leaving group. So the nucleophile here was initially negative, so you show partial negative. The bromine here, you're not supposed to look there. You're supposed to look here at the product side. So you see a negative, partial negative here. Okay. And yeah, backside attack. This is something that I'm still not sure about. Not gonna lie, I might actually be cooked if I'm tasked to draw. Uh, so given this, how do I show the backside attack? How this is supposed to be drawn? So okay, wait. Yeah, that's confusing. Stereochemistry, enantiomers, chirality. Um, that's confusing. I never really liked mirrors, so anyways, moving on. The leaving group will have enough space to depart as what's this? As you form the bond between nucleophile and carbon. Hang on. Ah, okay. I think backside attack makes more sense now. So when you say backside attack, the nucleophile attacks the electrophilic carbon coming from the side opposite the leaving group. The leaving group is bromine, right? So if uh, if the figure were to be like this, so Nu, and then bromine is over here. If it was like this, you cannot show the Sn2 reaction because again, Sn2 reaction is only possible if there is backside attack. Yeah, it's this one. If the leaving group and nucleophile are in front of each other, that's what I just drew. So any oxygen species with a positive charge is called an oxonium ion. So that's been mentioned earlier, no? So you would assume that this oxonium ion would be a leaving group. That's exactly what we see in this scenario. So this is not the final answer yet. You see an oxonium ion. This is still a leaving group. You still have to find the actual final product. So yeah, oxonium ion tells you that the reaction is not finished yet because it's still a leaving group. An oxonium ion is composed of alcohol and strong acid. So let's go to stereochemistry. So all Sn2 reactions proceed with the backside attack of the nucleophile. It's the nucleophile that attacks, okay, not the leaving group. Don't get it confused. They result in inversion of configuration. This is what I was referring to earlier. Inversion of configuration. So coming from this figure, you have this. So how to draw inversion of configuration? Yeah, okay. Um, so let's see this example. Nucleophile, oops. And then we have, okay, so this, we can perform backside attack because bromine is facing at the back. So in place we have Nu. Okay, so that makes sense. And then the bromine is, just imagine the nucleophile, this is a car. The driver is bromine. So the nucleophile attempts grand theft. So it tries to hijack the car. And that's exactly what it did. And it drove the other way around. And the bromine is left on the road. So, you know, hijack victim. That's just one way of imagining how inversion of configuration is supposed to look like. So the car will drive the other way around. Or just try to memorize this kind of example and assimilate with a similar scenario that you might see in the exam. So I think you can also get it from there. Let's check this example. So this is our nucleophile, no? SH. What's SH? Sulfur what? Thiol. Not, yeah, it's called thiol. Okay. Inversion of configuration. Like that, like that. Symmetry. Shade over here, shade over there. Back, back. And then like that. And then just replace. So common sense will tell you, if you have iodine here, the nucleophile will attack the carbon. So what you have here is SH. I is left alone. Okay. Next example. I wouldn't draw it like this. Maybe another render is 2, 3, 4. Oh wait, sorry. This time we have the nucleophile. 1, 2, 3, 4. Yes, that makes sense. And then plus Cl 1, 2, 3, 4, 5, 6, 7, 8 minus sign. So I believe this figure is the same as this. Just to avoid confusion, using the same logic that has been used in the past two examples in how the inversion of configuration was drawn or was shown, we just draw a mirrored image of this. Which is this. Okay. Okay, this is something that I don't like. Okay, we have the nucleophile, which is hydroxide. we have chlorine, the leaving group. It attacks this carbon, the nucleophile, and arrow to the chlorine. Okay, so OH is now here, and H. Okay, yeah. At this point, just try to memorize the figures. Then from there, you might be able to understand the pattern. So the hydrogen here was placed here when the nucleophile arrived here, and the leaving group was ousted or purged. Okay, some more examples. So this is the nucleophile, no? So you don't just unlike the NaOH earlier, we considered Na as a spectator ion. But in this case, CH2, CH3, the hydrocarbon is not considered spectator ion. Is there a reason? Is there a basis on what decides if what's connected to the nucleophile is a spectator ion or not? Let's see. What defines a spectator ion? Another question is, are hydrocarbons spectator ions? They are not. I saw a scenario earlier wherein it was also not considered a spectator ion. We also brought it together with the I think that was this, the OH, H2O. So it's the entire thing that's considered a nucleophile, not just oxygen. Okay, don't get it confused. For number 2, okay, the nucleophile is water. A good nucleophile because it is. Oh wait, no. Good leaving group is water, right? Yeah, but here, water is not acting as a leaving group. It is the nucleophile. And what determines a good nucleophile is basically if it's negative, then it is good. But H2O is not negative, so it's a neutral nucleophile. And you place an arrow to the carbon, and then arrow to bromine coming from the same line. So this is not the final reaction yet, the final answer yet, because again, you find yourself with an oxonium ion, oxygen that is positively charged. So you add water, and you end up with this. So it becomes the aromatic, the cyclo, and then OH, and don't forget the Br as well. I'm just not sure where the water and the H would go afterwards. Okay, number 3. Okay. This one is technically considered a nucleophile also. You see a negative, no? And then iodine. Iodine is, what's this, positive? Why is it positive? I wonder. Anyways, 1, 2, 3, 4. So yeah, this might be a confusing example for me. Number 4, bromine. This is our nucleophile. It's neutral. Um, bromine is negative. Okay, this makes sense. Number 5. So this basically means there's more than one reaction. So it's a two-step reaction. When you apply hydrogen, you get basically the substituent here is water, becomes water. And when you add this one, the thiol, again, the hydrogen here is part of thiol. I mean, in the sense that it is not a spectator ion. So SH is placed here. Water is the leaving group. It is a good leaving group because it is it's a weak base. Okay. That's it. That's it. For example 5. What is this? OH, H plus. Ah, so we have water again, an oxonium ion. We have a nucleophile. So substitute, the leaving group is water. Okay, this makes sense. This makes sense. Also, in this lesson, you have to know if there would be a reaction or not. There is no reaction. There is no Sn2 reaction if, again, the nucleophile and leaving group are facing facing at their front. In other words, there is no backside attack that will happen. I think that's one way to see if there's a reaction or not with what we have learned so far. How to determine if there is a reaction or not, Sn2. Also, if there's, when it says will there be a reaction, an Sn2 reaction in a certain substrate, it also depends on the substrate. Where is that? It's actually here. So this is another trend that you have to know. More on that later. Just to let you know, for now, Sn2 reactions only occur in certain kinds of substrates. Okay. Okay, here, what this reaction is not possible. Why is it not possible? So aside from backside attack, considering backside attack, whether it's it could be done, it also depends on the basicity of the leaving group. So water is a better leaving group. Here, the OH is a strong base, right? And as a leaving group, it's not a good one since it is a strong base. It is a good nucleophile, but right now the OH is not acting as a nucleophile. Usually when you see this kind of reaction, it will not react anymore. If you see something like this, it could still react. Aside from water, what are other good leaving groups that that basically says further reaction is possible? Again, we have bromine, chlorine, iodine. What if fluorine is here? The reaction is not possible. Why? because fluorine is a bad leaving group. Not because maybe because it's more basic. It has greater basicity compared to bromine, chlorine, iodine. But the better answer is because it is the most electronegative element, and yeah, it's not that easy to separate it from where it's connected to because of its high electronegativity. Okay, it all goes down to this list again. You have to be familiar. These are the good leaving groups. When you see these in any of these in a reactant regarding SN2 reaction, you know that it's possible for a reaction to occur. Okay? If you have a if you see a bad leaving group, basically composed of strong bases, a reaction may not occur. Okay? Okay. So yeah, I'll stop here for now. We have already finished SN2 reaction. We'll do SN1 and then uh, after that, comparing SN2 and SN1 and this is a lot. Assessing phili- nucleophilicity E1, E2. Okay. Yeah, we're almost there. I'm gaslighting myself. We're only at the third page. Okay, I'll end this video for now.